Welcome back. In our last lecture, we have seen the first physical property which is used to study the molecular structure, and that one is molar refraction. And we have also seen that how by using molar refraction the different simple molecules are confirmed by evaluating the molar refraction values and comparing it with experimentally observed. In continuation with that, we consider here a homologous series and their molar refraction values. Here methyl alcohol, ethyl alcohol, propyl alcohol, butyl alcohol and pentyl alcohol. So here you will find methanol, ethanol, propanol, butanol, pentanol, and here the difference in between the two structures, if you consider, the one CH2 group is added in the next subsequent molecule. One CH2 group is added. The values of molar refraction calculated are 8.218, 12.739, 17.515, 22.130, 26.744. And if you find the corresponding difference between these two values is found to be 4.521, between these two values is 4.676, between these two values is 4.615, and these two values 4.614. It means here you find approximately the change in molar refraction is around 4.6, due to the addition of one CH2 group, So we find here also in this example the molar refraction is additive property, and 4.6 approximate value is added for the addition of one CH2 group in this homologous series. Now consider the another example, another series, C6H14, C8H18, C10H22, C12H26. Here you will find carbon 6 and 8, 2 is added, and hydrogen 14, 18, 4 are added. So C2H4 group added in the subsequent molecule is C2H4, and here in the previous series it is CH2, and here it is C2H4, means 2 times CH2, isn't it? C2H4 means 2 times CH2, and the values of molar refractions are represented here. We find again the difference between the molar refraction values for this homologous series again, and here again it is 2 times the 4.6 approximate value that we have seen in the previous example. Here 2 times CH2 group means 2 times 4.641, 2 times 4.670, 2 times 4.672. Means approximately we have again find here the value added 2 times 4.6 approximately. So it is confirmed here the molar refraction is additive property. In the subsequent examples, we find how molar refraction is constitutive property. Constitutive property means how the constitution of that molecule is made. Constitution means the particular oxygen, suppose in this example, is hydroxyl or aldehyde. Now here the molecular formula is C3H6O, and this molecular formula having the two structures, one is related towards amyl alcohol Another is related towards propyl aldehyde. For amyl alcohol, the structure known is this. For propyl aldehyde, the known structure is this. Calculated molar refraction values are 17.112 and 16.065 respectively, and observed values are 16.973 and 15.950. Means the calculated and observed values are very close to each other. Here 17 and here 16.9 means around 17. Here 16 and 15.95 means around 16. Means the observed values and calculated values are very closely related to each other. And you will find that when this particular compound is having its alcoholic structure, then the value is higher, calculated as well as observed. Well, if this particular structure is having aldehydic structure, then the values are smaller. Means the smaller the values of a given liquid, the particular isomer is propyl aldehyde, and if the value is higher, that is suppose observed or also calculated for the given liquid, then the particular isomer is allyl alcohol. It means how the constitution is there, that is important in this particular example. Now consider the another example here that we find diallyl, and another, the name of it is isodiallyl. See now, here the diallyl, the two double bonds are there. Those are at the two ends. Now see, 1, 2, 3, 4, 5, 6. 6 carbon atoms. Isodiallyl 1, 2, 3, 4, 5, 6. Again 6 carbon atoms. And if you measure again here also the hydrogens, you will find both are diallyl and isodiallyl. These are again isomers of each other. With the molecular formula is same, structural formula are different. Here in the diallyl, the two double bonds are at the two ends, while in isodiallyl, the double bonds, carbon-carbon double bonds are in the alternate fashion. Single bond, double bond, single bond, double bond, single bond. Means these double bonds are in the, or single bonds are in the alternate fashions. While here double bond, single, single, single and then double. Means here the trend is not in the alternate fashion that you find here. So for these two different isomers, if you consider the calculated values, they are for both, they are 28.78, 28.78. But observed value, these are the two different chemical compounds, and observed value is for one it is 28.71 and that for other it is 29.87. It is higher by 1.09. Higher by 1.09. Here you will find only the two double bonds are there and they are in the alternate fashion. If three double bonds are there in the alternate fashion, in the long chain compounds, you will find this difference is again more. If four double bonds in the long chain compounds in the alternate fashion, again this difference is more. It means you will find that whenever the double bonds are in the alternate fashion, the observed values are higher than the expected value. These are the expected value and these are the observed value. Observed values are higher, and this increase in the molar refraction values due to the presence of alternate double bonds is called as optical exaltation effect. Optical exaltation effect. The constitution of this molecule and constitution of this molecule is different. How they are made? The different single bonds are different double bonds. Number of the single bonds here, those are equal, or here three single bonds, here also three single bonds, here two double bonds, here two double bonds, but their constitution is different. And that's why one may consider here also that molar refraction is constitutive property. Constitutive property means how the molecule is constituted. That is important here. And as far as the double bonds are considered and the values expected are suppose same but observed are higher, and this is known as optical exaltation effect here. So from these examples we have proved that how this molar refraction is partly additive. Now not fully additive, partly additive and partly constitutive property. So this we consider here. Now the molar refraction values for the gaseous molecules and the liquids of the same compounds is similar. But how the molar refraction values of solids are determined, that is important. For that, a suitable solvent is taken and the solid is allowed to dissolve in that particular suitable solvent. So a clear solution is obtained. And after that, the value of refractive index, is measured. The value of density of the solution is measured, and this 1 suffix is related towards the solvent and 2 suffix is related towards the solute. So here we consider molecular weight of solvent, molecular weight of solute. N1 is the molar fraction of here solvent and N2 is the molar fraction of solute. So N is the refractive index of solution. So now all the terms that we know from this particular formulation, and to the left hand side, extreme left hand side, we find R suffix 1, 2, R1, 2, and this indicates the molar refraction value for solution. Here it is not represented as a SOL solution, but here it is represented as R1, 2. 1 that for solvent always and 2 that for solute always. It is the representation generally. Now this formula is represented in the short way as R12 equal to N1 from this and R1 from the remaining parameter, N2 this and R2 from the remaining parameter. So what is R1? R1 is the molar refraction of solvent and R2 is molar refraction of solute. So R2 molar refraction of solute can be evaluated here. So this can be evaluated by rearranging this particular formula. So R12, which can be measured from this known things, because mole fraction can be evaluated N1, number of moles of solvent divided by total moles, number of moles of solute divided by total moles, so that becomes the mole fraction. So N1 and N2 can be evaluated. M1 and M2 are known. Density of solution can be experimentally measured. N of solution, refractive index of solution can be experimentally measured. So R12 can be experimentally measured. So R12 is known. N1 is known, R1 is known, N2 is known. So R2 can be evaluated. So in this way, molar refraction of solids can be evaluated by selecting a suitable solvent. So in this way, this is the one method that we consider. So we represent here, suppose this hydrogen molecule. What is there in hydrogen molecule? Center of positive charge and center of negative charge. They are in the same place. So there is no separation of center of negative charge and center of positive charge. And that's why here it is non-polar molecule. Here one hydrogen, one can represent. Here a single bond. Here another hydrogen, one can represent, isn't it? So what we represent here? Hydrogen molecule. Center of positive charge and center of negative charge, there is at the same place, that is at the center of gravity of this molecule. And the center of gravity will be represented by plus and minus signs together. Plus sign that for nuclei, minus sign that for electron cloud. So electron cloud that for both the hydrogen atoms, and this positive sign that for nuclei of these both hydrogen atoms. Similarly that for chlorine, that for nitrogen. Now that for CO2. How we can represent this? We know this is C and O2, these two oxygens. I am just representing here. Okay. Now let us assume that the distance of separation between the oxygen and carbon towards the left hand side and towards the right hand side of this with respect to this carbon are equal. And here this is the electropositive atom, this is the electronegative. So here this CO bond is polar. This CO bond is also polar. But you will find that the dipole moment you can represent for this CO bond is in this direction. The tail is towards the electropositive atom. For this particular CO bond also we can represent the dipole moment. So it is directed towards left hand side, it is directed towards right hand side. The magnitude of this dipole moment is same as the magnitude of this dipole moment, but only the directions are different. So one is plus, another is minus. That's why overall dipole moment of this molecule is 0. Overall dipole moment of this molecule is 0 because magnitudes are added together. Here one is positive and one is negative, and that's why here you will get for this molecule, though one bond is polar. Here in case of CH4 also, CH bond is polar. The polarity of carbon and that of hydrogen are different, and that's why here CH4 we know its structure. It is tetrahedral structure which is highly symmetric in nature. The resultant dipole moment for this particular molecule is also 0 because dipole moment for each CH bond get cancels together with the remaining 3, and that's why again here it is dipole moment is 0. For this molecule dipole moment is 0 because all these carbons and all these hydrogens in the benzene ring are planar. All these carbon and all these hydrogen lie in a one and the same plane, and that's why here again the dipole moment is 0. That's why the dipole moment 0 molecules are non-polar. If you consider this as the polar molecules, then also you will find hydrogen is electropositive, chlorine is electronegative. The total molecule you will find it is polar because the dipole moment is non-zero. Another concept for the same, and that one is how this particular dipole moment is accounted the diatomic molecules. Now consider this diatomic molecule, hydrogen chloride, hydrogen electropositive, chlorine electronegative. So sign is represented as charge, del negative, del positive. Sometimes it is represented as a Q plus positive charge, Q minus negative charge. The distance between the separation between these two nuclei, one that of hydrogen and another that of chlorine, from the center of this nucleus is R. That we call it is the bond length also. This bond length is sometimes represented by R, sometimes it is represented by a small letter D, sometimes it is represented by a small letter L. So mu is the notation for dipole moment. Mu is equal to Q, that is the charge. This Q plus and Q minus, both charges are same, but only here one is positive, another is negative. Magnitudes are same, signs are different. That's why separated charge is Q and distance of separation between the two charges is R here. Sometimes it is represented by suppose D and sometimes it is represented by L. So here we consider the bond dipole moment is a vector quantity. Vector means it has both magnitude as well as direction. Magnitude, this length of the arrow itself indicates the magnitude. If the length is small, smaller the magnitude. If the length is greater, more is the magnitude of dipole moment. And this arrow head indicates the direction of dipole moment. This head is always towards electronegative atom or charge, while the tail or positive sign is towards this electropositive atom in that particular molecule. Now we also consider, so what is this dipole moment? A dipole moment arises in any system or molecules in which there is a separation of charges. They can therefore arise in ionic bonds as well as in covalent bonds. Dipole moment occurs due to difference in electronegativity between two chemically bonded atoms. A bond dipole moment is a measure of polarity of a chemical bond between two atoms in a molecule. It involves the concept of electric dipole moment, which is measure of separation of negative and positive charges in the system. Now we consider this example. As we have seen previously, the one non-polar molecule CO2, which is linear. Here we consider the BF2, beryllium fluoride molecule. Here the bond angle between the two beryllium fluoride bond is 180 degree. Fluorine being more electronegative. Atom shifts the electron density towards itself. That's why the dipole moment is represented and directing towards F. This is also representing and directing towards F. This is the separation distance bond between the F and F in this particular molecule. And this total bond moment. So this is the dipole moment of one BF molecule, dipole moment of another BF molecule. Both are non-zero. So this is non-zero, but summation that we'll get is 0 because they are of equal magnitude but opposite sign. And that's why one cancels with other and we get the resultant value of a dipole moment as 0. So this is the very good example that we consider, and which one is the linear molecule, 180 degree angle between the two beryllium fluorine bonds. Similarly, in case of CO2, in two CO bonds also the bond angle is 180 degree. So in this way we consider how by using the dipole moment property, the structures of the molecules in terms of also the polar or non-polar molecules can be understood easily. So we summarize here that in this particular lecture we cover that how the molar refraction is partly additive and partly constitutive property. Similarly, we consider the very important physical second property, and that one is dipole moment, which is represented by mu. In our next lecture, in continuation of this dipole moment term, we consider how it is evaluated, what is the unit of dipole moment, and how it is measured experimentally, the different methods for the measurement of dipole moment, and then we continue how it is related towards the structure of the molecules. Today we stop here. Thank you.